Hello, everyone. Happy New Year. Okay, welcome to the OpenFOAM and the combustion simulation webinar. So this is the first webinar in the new year, and this is also the 30th webinar since we started last March. Okay, so today we are very happy to have Professor Bosen Wang to give us a talk about LES large area simulation of spray optimization by using explicit volume diffusion method. Okay, so before the talk, I will first introduce Professor Wang. So Professor Wang has been appointed as associate professor in the Institute for Aero Engine at the Beihang University in China since November 2021. Prior to the academic career at Beihang University, he served as a postdoctoral research associate in the clean combustion lab at the University of Sydney since the beginning of 2020, and in the Institute of Combustion Technology at the University of Stuttgart in 2019. Professor Wang got his PhD degree at the University of Stuttgart in 2018. His main research area is about theoretical modeling of turbulent multiphase flows and combustion, and its application to combustion chambers by supercomputing techniques. Currently, Professor Wang's research is mainly funded by the Aero Engine Corporation of China, AECC. Okay, so now the time is yours, Professor Wang.
Okay, thank you, Professor Zhang. It's a great honor to give a talk here, and we can discuss with the panelists and the audiences who are interested in my work, and we can discuss further in the future and find collaborations. Okay, now let's start. My name is Bosen Wang from the Aero Engine Combustion team in the Institute for Aero Engine, Beihang University, BUAA, from Beijing, China. Today, I will talk about LES of spray atomization by using an explicit volume diffusion EVD method. The outline is here. First is the background, and the second, I will talk about the existing method for the spray atomization, and then I will give an initiative method. The name is a novel explicit volume diffusion method, and continuing, I will couple the EVD with sigma Y model, and then I will talk about the implementation of the LES EVD and the validation. The validation cases including the different cases at different Reynolds numbers, from the low Weber number, really plateau instability, to the medium air blast atomization and high Weber number jet in cross flow. And the next section, I will talk about my some ongoing modeling work and result. Only some simple work and result, some simple graphics. And at last, I will talk about the outlook and acknowledgement. First, the background. When we talk about atomization, we cannot avoid the combustion. We know from my or from a conventional distinguishment methods, this process can be separated into a primary atomization period and a secondary atomization and a spray combustion. In the primary atomization, we know the interface instability first dominates this process, and then the jet break up, and then we have various shapes of fragments, then the ligaments, they can collision and coalescence, and then we also can have evaporation in the primary atomization stage when the inflow temperature is very high. And the evaporation occurs until continuing in the secondary atomization stage. And in this stage, big fragments and ligaments continue to break up to the small spherical or close to spherical droplets. And in the consequent stage, the evaporation and combustion will dominate. And in this process, we will first see the external and internal group combustion. And in the practical applications, we will seldom see some single droplet combustions. And in these three stages, another separation regime is we can define the dense regime and the dilute regime. In the dense regime, usually a Euro concept we use is volume fraction, where the volume fraction is larger than 0.1%. And for the dilute regime, the volume fraction is smaller than 0.1%. And continuing for the turbulent spray combustion, dense spray is a bottleneck. First, we can start from the current cutting edge workshops on turbulent combustion and sprays. Since 2019, the workshop has focused on the dense spray and spray atomization. And due to the absence of the accurate measurements and the predictive models, now the workshop focuses on the key scientific questions about how atomization influences both the dense spray region and the dilute regions. And the three typical benchmark burners are presented in this workshop and encourage the people to work on it and to do comparisons, including the Sydney needle spray burner and the Korea Ruan spray burner and the Cambridge swirl spray burners. And I will talk another background about the progress on numerical combustion of combustion chamber in China. And in 4 years ago, people from industry and Beihang University and Tsinghua University, as we know, Professor Yuan from the last talk, also gave a reviewed paper on this topic. And they pointed out the explanation and the prediction of the atomization mechanism for both of the main combustor and the afterburner in the air engine are not mature yet. And very, very expensive simulations can give a scope of what's ongoing there. And another thing is from our team. I will present the LPP combustor concept in our team. And its key technology is about the TELESS burner. The TELESS means the technology of low emission of stirred swirl. And this stirred swirl enhanced atomization mixing leads to the high performance combustion and high stability of combustion in the combustion chamber, and also the low emission of NOx and CO as the outlet of the chamber. And we will see this is the picture from the experiments in our group, the PLEAF image and the PMIA image in the channel of in the swirl channel. And in the downstream, we will see different parameters of the inlets and the geometric parameters will lead to different combustion performance, even lead to the combustion instability there. And we have concluded that spray atomization and evaporation at high pressure and temperature in the swirl channel is the most sensitive factor to the flame stability and the pollutant emission. Now, let's talk about the key issues for different regimes. Here, this is a very classical picture from scientists and the co-workers. in 2015 PCI paper. This is a very well clarified graphic about the spray atomization to the combustion. As we know, in the scientific research field, most turbulent spray flame still stays in the dilute spray stream, spray regime, and it can be characterized by the droplet Larden flow. Yeah, the droplet Larden flow. We can see droplet one by one, and there's a turbulent reaction there. And the simplification is for this region, or the simplification can be accepted is turbulence can determine the flame. Yeah, and in the one region upstream is we will see the group combustion. This is the most phenomenon we will see in the practical applications before the evaporation evaporate and burn out. We will mostly see group combustion. And in this region, we will have the evaporation and the turbulence coupled mixing determines the flame. And the regime is still the droplet Larden flow. And there are also turbulent reactions. And the upstream further is the secondary atomization. In this regime, another atomization process as we progress, as we have just defined is introduced is the primary atomization. And there's one difference between them two is, from my perspective, in the secondary atomization, the turbulent dispersion dominate the discrete phase and the multi-shapes droplet movement, and also clearing, coalescence, evaporation. But in the primary atomization, I would say is the interfacial flow regime is a dominant one. And the interface and discrete phase are mixed in this region. And the transition between them is also a remaining challenge. And now let's talk about the modeling of atomization and combustion. When we talk about turbulence modeling, we know the DNS and LES for the high fidelity numerical simulations. In the DNS, the grid is very refined and it can resolve all the scales. And in the large eddy simulations, only the large scale are resolved, and the computational costs are relatively saved. And in the turbulence and single phase turbulence combustion, as well as the dilute spray combustion, the subgrid models are well developed. And the turbulent viscosity model and the various turbulent combustion models are used here. But for the turbulent multi-phase flows, additional small scales induced by interface and the droplets come in, and they bring here lots of scales even smaller than the smallest turbulence scales at the interface, like the evaporation and the mixing there, and even the clearing coalescence there. And we can see we can use the von Karman-Paul spectrum to give an interpretation. Here is the single phase flow, or single phase. This is a single phase flow. We can see in a turbulence in turbulence, and in the LES simulations, the most of about 80% of the energy are resolved, and the SGS model only give a model for 20%, very low turbulent energy. Well, when the chemical reaction occurs, we will see the energy, the chemical reaction energy. Most of it here is in the subgrid model. Yeah, then we will know the chemical reaction is a very small scale, occurs at very small scales. And then when we have evaporation, and for the dilute regime, usually we will see here is a regime, and here is a droplet, here is another droplet, and the distance of them is far away. And usually we only have single droplets in one SGS scale or subrange scale. But in the dense regime, we will have multiple droplets in the subrange scale. And here we will see in the subgrade scales, we need to model the evaporation coupled with the turbulence for the mixing here. And if we have interface, in the interface means we usually do not have smallest scales. Yeah, we also tested in the single phase flow. Here is a dissipation scale. We call it a Kolmogorov scale. But when we have interface, there's we don't have anymore the smallest scales, no dissipation scales anymore. Since this means in the simulations, we cannot have numerical conversion. Yeah, I will speak detailedly in folly. Let's see the current numerical methods for interface flows. We know level set and diffuse interface. But currently, as I know, for the LES, for the application for the LES spray atomization, the WLF methods is in the front area. Mainly because it's intrinsic conservation of mass and the numerical stability. But it has shortage. One shortage is we see the volume fraction transport equation. It has no diffusion term, only time derivative and convection term, which means we shouldn't have alpha between 0 and 1 for the physical meaning of this equation. And then when we use discretization, that means we will have significant numerical diffusion. Yeah, the numerical diffusion leads to the alpha 0 and 1 in the computational domain. So then most of the WLF simulations are limited in the DNS. We need to use extremely refined grid. But even like this, the interface can never be resolved maybe I need to give a condition. It's in the subcritical condition. Yeah, no smallest scales and no greater convergence. This is a test by myself. This is a two-dimensional simulation with 2,400 times 4,000 cells in this region, and the boundary thickness is about 45 grid cells. We still have we still have the numerical simulation, and to avoid or to alleviate the effect of the numerical simulation, people invented the geometric WLF method, including the surface sharpening and the surface sharpening and the surface reconstruction to reduce the numerical diffusion. As we know, the artificial compression method in the interform, OpenFOAM, and the interface reconstruction method, iso vector solver. And I also do a test here. This is artificial compression, and this is iso vector. We will see at a very refined grid, the cells between 0 and 1 are almost vanishing, and they show a very close result. And then we can give a conclusion. The DNS is extremely expensive, and we can see Professor Kun Luo's paper from PECS in 2019. They give a summary of the spray atomization simulations from 2007 to 2019. We will see most of simulations need at least tens of millions of cells, and at least 1,000 CPU for high performance computation. And now currently it is in lack of LES with rigorous physical interpretation. What does the rigorous physical interpretation mean? This is a jet. This is a jet. In single phase flow, we know this is turbulence fluctuation. But when we have interface, then that means we have interface induced fluctuations are not cared a lot previously. And another problem is the numerical diffusion, as I mentioned. And the second, the last one is the subgrade surface tension force. This is a very high nonlinear term. And the result here in 2014 from Salvador Navarro Martinez from Imperial College, they show the high grade sensitivity of the LES or VOF method. And compared with LES of single phase flows, a consensus of LES or interfacial flows hasn't been reached yet in the research community. I will introduce two methods now currently often used. First is the turbulent filtered VOF model. It's a very easy concept. We know this is a mass conservation equation and the momentum transport equation, and the additional term is the surface tension force, and the next term is the volume fraction transport equation. And they just use turbulent diffusion model to close the sub-volume sub-filter flux. And the problem here is they neglect the fluctuations induced by the interface. They still only consider the turbulence. And the numerical diffusion is significant due to no molecular diffusion. And here for the subgrid models, the problems include the subgrid fluctuations of density and the viscosity are usually neglected. I don't know why. But this problem can be avoided by the density filtering. And another problem is the grid sensitivity of the surface tension force. They just use the resolved value to model the surface tension force. Another method is compensate for the TF-VOF method. It's called the TFAC method. It's turbulence filtering and artificial compression. That means, okay, they don't think only the turbulence filtering or turbulence models, viscosity models can model the subfilter flux. And they also use artificial compression to model the interface. They define a criterion, the criterion IRQK, and it's defined by the product of the resolved curvature and the grid size. And if this factor is smaller than a critical value, then the C alpha equals 1. That means the turbulent dispersion dominant. And if it is bigger than a value, then C alpha equals 0. And that means the turbulent dispersion is switched off. We only have the interface sharpening. And the problem here is the CR here in this model seems highly dependent on grades. This is an algorithm in the interform in OpenFOAM. The CR value is recommended from 1 to 4 by Yasaki and Henry-Vella. And another thing is this criterion is highly dependent on the grades. This is a test by myself. The black point means where the interface sharpening occurs. And the test of the grid convergence I will show later. So this is the motivation. The requirements of high quality large eddy simulations. Here we need the rigorous physical meanings of average equations and the subgrid models, and we also make sure it has great convergence and accurate predictions. Okay, then we define a volume averaging concept. This volume is a physical volume. Yeah, it's not a grid, it's a physical volume. It's centered at a point x0 with the length scales of volume of its volume one third to one third order, and the Reynolds volume average and the Farber volume average can be defined here, similar to the turbulence filtering. And then we use the Farber volume average, and then we have the mass continuity equation, the volume average, the transport equation, and the volume, and also sub volume flux. Then we can define the sub volume fluctuations, and then we also can define the density and the viscosity by the volume average concept. And another thing is the Reynolds volume average, the volume fraction can be defined in this way due to the mass conservation. The volume it's the volume-based volume fraction times the mass equals the times the liquid density, or the liquid mass equals the average density times the mass density average alpha. Then we need to first close the sub-volume flux. We use a bimodal PDF concept to close it. Okay, since we don't accept the turbulence filter, we use the we separate the one volume into a liquid part and a gas part, liquid part and the gas part. Then we will have the volume sub-volume flux equals the density times the alpha times 1 minus alpha times relative velocity of the two phases. Okay, this is very interesting. This equation very, very interesting. We will have 3 indications here. The first thing is this equation tells us the sub-volume flux is induced by the mean drift velocity. This is the mean drift velocity and the inhomogeneity of the phases. And the second point is the sub-volume flux is 0. The sub-volume flux is 0 in pure fluids. In pure fluids, no matter alpha equals 1 or 0, this is 0. And another implicit information, if we do a mathematical calculation of this term, we can find it approaches 0 in the region before interface instabilities occur, or before the curvature occur. Even though the mean drift velocity and the homogeneous phases exist. Even this exists, there's no sub-volume flux here. So that means the sub-volume flux is also related to the coherent structure of the interface. And then we continue use the bimodal PDF concept to close the mean drift velocity and use a gradient diffusion term to approximate this term. And we also introduce a Q criterion coherent structure factor to close this volume diffusion model. And we can see the 3 parts in this model can satisfy the requirement of this the indications of this sub-volume flux term. The first term means, okay, here it can make sure the sub-volume flux is induced by the mean drift velocity, because we find that the mean drift velocity also very close to proportional scalar shape of the strain rate. And the second part can satisfy the subvolume flux equals 0 in the pure fluids. And this coherent structure term is Q divided E. The order of 3 divided 2 is to make sure the coherent structure of the interface to dominate the subvolume flux at this specific region. And then we need to close the subvolume viscosity. The subvolume viscosity, we still introduce the volume speed lemma, and also effective turbulent viscosity. Yeah, and we know in the interface region, EV is not equal 0. Yeah, from the last slide. So this dV times the speed lemma can give the volume viscosity. But in the pure fluids, dV equals 0, such that the volume viscosity is 0. But in the pure fluid, we cannot forget the turbulence still exists, and the turbulent viscosity is needed. But this turbulent viscosity, we need to make sure it can smoothly transition to the interface region. Then we introduce interface determinator, and then we can have a 0 of the viscosity in the middle of the region. There, the volume viscosity dominates, and in the turbulence in the pure fluids, this is the factor is 0. Then we only have turbulent viscosity. Then we will have a very smooth profile of the subvolume viscosity. And the next term is the volume average the surface tension force. This surface tension force, we go back to its original form. We do a volume average of it, and then we give the definition of curvature of the nabla of the normal direction of the surface, and the normal direction of the interface can be defined by the gradient of alpha, and delta S is the interface detector. We introduced a n-1 dimensional Hausdorff approach to close this term. Yeah, we will see this term. Yeah, this term we do a volume average. Yeah, we first do a volume integral and then divide a volume. We will have, then we use we apply this approach. We can have we can transfer it to a surface integral value, and then we do approximation. We will have averaged volume average curvature. Yeah, the resolved curvature, a resolved direction, and times interface, the total area of the interface. But we cannot forget the total area. The interface is wrinkled. It's wrinkled, and the total area can be modeled by the surface density times V, a volume. Surface density times a volume we can have the total area of the interface, wrinkled interface. And how to model the surface density? Yeah, we brought the concept from the well-known premised flame combustion modeling and the surface wrinkling model. Yeah, we use the surface fractal dimensional concept to model it at the first attempt. But at the same time, this is an algebraic model. And alternatively, we can couple the surface, the sigma y model, where a surface density transport equation is solved. And we transport the surface density, and then to couple the surface density, to couple the surface tension force. Let's see how to couple the EVD with the sigma y model. We know the surface density, we still go to its original formula. The transport equation for the surface density is this term. Time derivative and the convection. The convective velocity should be the interface velocity. And then we separate the interface velocity into bulk velocity and their difference. And this difference can be approximately to the velocity between the high density phase, the velocity of the high density phase to minus the mean velocity. And we do this term we use bimodal concept. We can see it is the same as the volume flux. Yeah, this approximation exists when the big difference of the density for the two phases for this kind of condition. And then we can have this transport equation, the volume diffusion transport equation, and there is a volume diffusion of the surface density and the source term here. And this equation is usually not solved directly. The surface density usually can be divided into a sub-volume dynamic surface density and an intrinsic minimum value. This intrinsic minimum value is related to the volume fraction times its 1 minus volume fraction and square root divide volume scale. And this term, it has the key thing is the source term, and this source term has a physical meaning of the interface broke up, and the interface interface increase and decrease due to breakup and coalescence. And it is modeled by introducing a critical surface density. And this critical surface density is related to a critical Weber number. And how to implement this EVD method? Yeah, because the physical equations here seems no difference here. We still only have volume diffusion, and for the volume fraction the same, volume fraction transport equation the same. We still didn't solve the problem due to the numerical diffusion. We only solved the rigorous physical meaning of this model, and now the implementation can give the solution how to overcome the effect of the numerical diffusion. This EVD method is developed based on OpenFOAM. It's called the EVD form. We introduce two scales. One is physical volume scale. Here we see the big red square. And another one is the LES gray scale, the small grid values, the relatively smaller values here. The grid side here. And for the physical volume scale, we do volume averaging there and modeling the sub-volume closures. And the LES grid is used to discretize volume average equations. So, and then the physical volume scale is based on our investigation. We found it needs to be the same order of the boundary thickness near the interface. And based on this physical volume scale, yeah, we define a sub-volume closures, the volume diffusion. Yeah, just now we gave the interpretation how we derive this dV, and then it can give a volume physical diffusion to diffuse the interface region to a volume scale. Yeah, we stretch this interface to a volume scale. And then we use the LES grayscale to resolve this secant interface. Yeah, then when we keep the physical volume scale the same as a constant value, and then we refine the grayscale. Yeah, the numerical diffusion inherent in the LES grid, and then will be smaller and smaller. And then at some point it will be overwhelmed by the physical diffusion defined by ourselves, and then we will have a grid convergence. Then we will give the test of the EVD. We give canonical shear layer cases for 5 cases for laminar and turbulent cases. We define a laminar and turbulent boundary layer thickness, and outer scale the shear flow. This is a very classical type, shear layer configuration. And these two are the similar, are in the same condition as the Aero-Hawkes, the shear layer equation, a shear layer case. And we found after one flow through time, it reach converge, and we collect statistics. And we do a priori analysis to validate our models, different volume scales. We found our models can capture the filtered DNS data, and then we apply these models to the LES simulations. First test case is the Sydney needle spray burner, the acetone air blast spray, and this is the image of the spray, and this is our LES result. The Reynolds number is 21,800, and the Weber number is the gas, based on the jet Weber number 35. Yeah, the jet Weber number, and then the experimental data are obtained by the two-angle backlit and the image slashing technique. And in our simulation, we only model the breakup in the central channel and no pallet. And the air blast turbulence intensity we get from the experiment is 11% and 15.4% for these two cases. And the liquid turbulence intensity is about 5% in the pipe flow. Now let's see the result. First, I show volume average volume fraction on the grid scales and the volume fraction on the volume scales. This is simulation on the 2.3 million LES cells. We see the liquid core pinched off, and this pinched off can also is not smeared out in the volume scale, and then it breaks up into various smaller fragments. Yeah, and then since we define the volume scale only as the order of the boundary layer thickness, and we see the only the interface region is smoothed. The fragments are not smeared out. And another thing is the key features of different types of fragments are not changed due to the volume average. And another graphic is about the surface density on the grid scale. We will see the grid surface density first increase due to the wrinkling because the instability occurs, and then in the downstream it starts to decrease due to the dispersion of the spray in the center line. The spray becomes the volume fraction becomes smaller, and also the surface density becomes smaller. Yeah. But for the downstream, we see the intermittency due to the discrete interfaces of different fragments. Then we'll see a demonstration of the volume diffusion model. Yeah, this is the volume diffusion model as we proposed. Yeah, we will see the volume diffusion increases smoothly, yeah, from zero before breakup. This is dominant by the interface coherent structure term. And before the interface instability occurs, the divergence of subvolume flux is close to zero. Yeah. So as we mentioned before, and this volume diffusion is required to be zero. Yeah, this is satisfied. This satisfies the physical world. And the second thing is the high turbulence intensity exists upstream, leading to the relative high velocities of the viscosity. Yeah, the viscosity still exists, but volume diffusion doesn't exist. And then the instability continue to form and grow, resulting in the gradual onset of the curvature and then increase the volume diffusion. Now, this is the result of the comparison with the experiment result, and also this also includes the numerical convergence. First, we see the mean and the RMS values of volume fraction present convergence, especially for the 2.3 and the 4.5 million LES cells. Yeah, we decrease the simulations of interface interfacial flow from tens of million to the 2.3 million LES cells. And then another thing is even for the 1.1 million cells, the difference is not too big. And an overall agreement of the mean profiles of the for the experiments and the numerical simulation data are presented. And some discrepancy can be seen here. This reason mainly because of the small is for the RMS. For the RMS value, the big value is at about 3 to 4 diameters downstream, and it can be captured well by the model. And but our model gives a bit high RMS value compared with the experimental data, but under prediction of the RMS downstream. But even for the RMS, we see a good convergence. And the similar convergence can be seen for the surface density. And as the jet breaks up, the surface density we see start to increase to the highest value of the RMS, about R x divided D equals 3. And from here downwards, it decreases due to the intermittency and radial dispersion. And then we also apply this method to another Weber number case, a higher Weber number case. The same grid resolution, same grid numbers, but smaller, only change smaller volume scales and the smaller grid scales near the interface due to the high Weber number and Reynolds number because it has a lower boundary thickness. And then we have also good prediction of the experiment results. And then we make a conclusion and also make a comparison and conclusion of our method and the existing methods, advanced method from Korea, Beihang University. Here I made a for the thinning needle spray burner. I first made a test for this method. We see a very high grid sensitivity, which is not tested before in their case, and also in their paper. But in our case, we see good convergence and accuracy. And then we do a Richardson extrapolation analysis. We see the EVD method presents a much lower GCI index, and we can conclude it has a rigorous physical meaning, low grade sensitivity, and the coarse grade but accuracy. The second test is relay plateau instability. Here we see a spray breakup and atomization in the stationary air environment. We see dripping, relay, wind-induced, and the wind atomization here. We see here for our relay plateau instability, we will test our case into to extreme low Weber velocity and Weber number. Here the jet diameter is about 2.51 millimeter from testing up in 2009. This is a canonical water jet in air breakup. And the mean jet velocity only 0.7 meter per second. And the boundary layer thickness is 398 micrometer. And we define 4 grid cells from 0.27 million to the 10 million cells. And then we give periodic boundary conditions to satisfy the breakup theory for the linear theory of the really plateau breakup. And then we know here this is our animation. Oh, sorry, yeah, the animation cannot here. This is the animation of our really plateau breakup process. We see here the breakup length is converged for the 4 grids, and the volume fraction also converged for the 4 grids here for the 3rd grid and the 4th grid. And then we make a comparison of the our numerical results with the linear stability theory. We see our result can capture well. We see the breakup length is converged for the 4 grids. Yeah, when we increase refined grid, we have converged. And also we have converged the volume fraction in the central line and also in the radial direction. And then we compare the breakup length captured by our numerical results and with the linear stability theory. We see our model is good to give the result. And then we give the result of breakup length growth rate versus the initial wave number of the inlet velocity. We see here some discrepancy for the high wave numbers. This is mainly due to the viscosity effect in the linear theory. For the ideal linear stability theory, viscosity is not considered. Here we have. And the second test is the spray in cross flow. Yeah. As we know, the Weber number and the momentum ratio can determine the map of the spray breakup and atomization in the cross flow. Yeah. And this is our the experimental case from the BOAACT lab. And we mainly focus the region in the shear breakup, and this is a typical gas turbine condition. And then I will give an example of the 4th case. The 4th case with cross Weber number is 223, and the momentum flux ratio is about 19 is here. And the jet Reynolds number is about 4,797, and the jet Weber number is also more than 4,000. This is our computational domain. This domain length is about 52.3 millimeter, and the upstream is about 20 millimeters, and downstream is 30 millimeters. We show this video of the breakup of the jets, and then we show the graphics of the instantaneous volume fraction field at 3 grids, and 1.6 million cells, 3.7 million cells and 7.3 million cells. And the same we see here from the qualitative comparison. Here is converged, and then we do a trajectory comparison. We see there is very low grade sensitivity, And then we also compare the trajectory captured by our simulation, this point, this line, and we compared it to the classical trajectory empirical equations. These two equations here, equation 2.4, 2.5, is in our document. Here we see this equation is relatively better for the model, and but overall our LES result can capture the classical empirical equation from hundreds of thousands of experimental data points. And this three in cross-flow, we continue to demonstrate its convergence. We define three positions here in the central jet and in the breakup point and in downstream. We see the volume fraction mean, a good volume fraction mean converge for the 3.7 million cells and the 7.3 million cells. Yeah, very good converge. And for the RMS, also show a good converge. And for the velocity mean, we see similar results. And then we do the consequent analysis by the low order POD analysis. This is the experimental result, experimental pictures from our experimental pictures. We collect them and then do the POD analysis. We see we get from the mode 1 to mode 12, and then we compare with our the POD of our LES results. We see due to our LES result cannot due to the low resolution, mainly because of low resolution. There is we can capture the trend, roughly the trend of the from mode 1 to mode 4. Yeah, the high with high energy mode. And another thing is in our analysis, we see the mode 3 and the mode 4 here. This point can capture, relative seems to review the jet breakup point here. And this is can also roughly captured by the POD analysis of our LES result. Next, I will show only some results ongoing. Yeah, these results are not published yet, so only some simple information and provide direction to discuss with one who are interested. We extended the EVD method to a multiple mapping conditioning stochastic particle framework for solving the droplet size distribution. Yeah, we use a stochastic particle to solve the sub-volume subgrid equation. We do the filtering density equation of the EVD equation. Yeah, just to remind, our volume diffusion has nothing to do with the turbulence. It's only induced by the relative velocity of the two phases. And then we do the stochastic particle formulation. And then we model we only model the source term for the surface density. Then we use the volume fraction surface density can get the D32 characterize droplet size in the sub-volume space. And currently, we implement the dense particle MFC model. We solve an independent reference variable on the particles to use based on this reference variable. We select the particle pairs and then apply the anisotropic mixing timescales to solve the mixing, the volume to mimic the volume diffusion and also mimic the diffusion between the two phases due to the existence of the volume. And then we test it on the semi-needle spray burner ES2. And we show the results of the from the particles. This is from the stochastic particles. And then we also get the target value from the stochastic particles due to the Euler-Lagrangian coupling, which is presented on the Eulerian grid. And another thing is we simulate Eulerian. This is the target value due to the kernel by kernel estimation we get from the particle values, which is embedded onto the Eulerian grid. And this one is we solve Eulerian equivalent volume fraction, which is coupled with the target value from the particle values. And then at last, we also solve Eulerian independent alpha. We do a comparison of this 4 statistics. We can get converge of these values. And this is a validation of the EVD MMC algorithm and the mass conservation. And this is outlook and acknowledgement. We will see the continue the first, the second page in our of the first several pages here. I introduced the current issues here. Three issues. What I mentioned is the group combustion, the evaporation, turbulence, coupled mixing, determined flame. This is what I gave a solution or give a model during my PhD work. I provide based on Kilimenko and the Bilger's model. I developed it as a Kolmogorov scale mixing model to close system. And another thing is here I presented the work in the interfacial regime dominant simulation, where the interface and decrease phase mixed. And the remaining challenge is a transition between these 2 stages. Yeah, this is the outlook in our future work. And here is acknowledgement. The contribution in this work by the following persons are acknowledged, including the Associate Professor Matthew Cleary at the university, and also Professor Asa Masri, Mr. Jiayue Yu, and Mr. Fakar Abbas, Mr. Tim Hare from the same university. And the initial discussions of the EVD concept with the following persons are acknowledged, including Professor Andreas Kronberg at the University of Stuttgart and Associate Professor Konstantina Volkizaki at the University of Brighton in the UK. And here is advertisement. We are recruiting PhD students and postdocs. The following topics can be selected, including the high fidelity numerical simulation for the next generation Aero engine combustor, and the LES of small black body spray combustor coupled with the new concept spray nozzles, and machine learning modeling for controlling the performance on combustion chamber, and modeling simulations of low carbon fuel combustion chamber, modeling of spray atomization and turbulent combustion flame, and also including soot and spray flame. And at last, machine learning chemistry coupled with stochastic particle models. Students and are very encouraged to contact with me. Are welcome, and the following topics all can be selected. And thank you for your attention. This is my email. Yeah, thank you, Wang. That's all for my presentation.
Okay, thank you very much, Professor Wang, for your very nice talk. Okay, so in the following, we will have the Q&A time. So for the audience, if you have any questions, you can submit through Q&A. And for the panelists, if you want to ask, please unmute yourself and discuss with Professor Wang directly. Okay. So is there any questions? Okay, maybe I ask first. So for the last part, you introduced the EVD and MMC model, right? So
this is the final part. Yeah.
Yeah, the final part. So with that method, you aim to predict the interface and as well as the
surface density and the volume fraction.
Yeah, full fraction, yes. And for the MMC part, so we can predict the droplets, right? Is my understanding correct or not?
Yes.
Okay, so I think there is somehow like a regime boundary, right? So in this method, how is this determined? Liquid, bulk free, and lots of the droplets there.
Yes. The droplet is characterized by the volume fraction value and the surface density value on the stochastic particles. There's no physical droplet there. Only the droplet size is soft on the notional particles, and this and the droplet size determined by the volume fraction surface density on the stochastic particles.
Okay.
And then we can collect the notional particles and know the distribution of the D32 on the notional particles.
Okay. Okay. Thank you very much. And now one question from the audience. So how to make the balance between the gas and liquid?
Maybe I didn't quite understand well the balance. What does balance mean?
So maybe this question is from Chun Lady, the grid. Okay. The grid balance.
Oh, the grid balance between the grid about. The grid balance means how much grid means how the grid resolution in the gas and the grid resolution on the liquid. I think so. Yeah, the grid size for the liquid and grid size on the gas. Okay, this is a good question. Yeah, I only mentioned the characteristic cell size is characteristic volume size. This method we care more about the volume size, the physical volume size. Yeah, this physical volume size we defined it close to relatively to the boundary layer thickness near the interface, and this interface boundary layer thickness can be determined by the Reynolds number of the jet and of the gas flow. And then we need to make sure the grid cells can resolve well of the physical volume scale as well as the boundary layer thickness. And then we refine as until we get the grid convergence. Yeah, and I can give you the value. After our test, we found the numerical convergence usually reach about 4 to 5. The volume cells about 4 to 5 of the grid size. That means the grid size, the characteristic grid size near the interface about 1/4 or 1/5 of the boundary layer thickness near the interface for our method. Yeah, this is the answer.
Okay.
I'm not sure whether I answered the question or not. Yeah.
Okay. Thank you very much. And
I also have a quick question.
Yeah, please go ahead.
I don't have a camera right now, but I found in the past in OpenFOAM, when you run pure gas phase simulations, that the backward time discretization can be more stable than the Crank-Nicholson scheme. But then when I run VOF simulations, sometimes the Crank-Nicholson scheme seems to be more stable than the backward scheme and also give better results. Do you have any recommendation or experiences on the time discretization for volume of fluid methods in OpenFOAM?
Let me repeat your question first. You mean the backward scheme? You mean the time derivative scheme or the spatial discretization?
The time derivative.
time derivative. Yeah, we made yes, we made a comparison. Yeah, we made a comparison. All it was asked by the reviewer to do a comparison in our rebuttal. I remember this. We show the results comparison between the backward and Nicholson and the Euler. We found for our case, for this kind of spree jet and for the LES simulations, since the grid is not refined a lot, we only have several millions of cells. And then in this kind of scales, a grid, we don't have numerical instability issues. This is what I can tell you. Maybe you can ask further what you mean more for this question, for this point.
Yeah, so to me, it seems like the behavior specifically in OpenFOAM changes between the pure gas phase combustion simulations and volume of fluid simulations, at least in my experience. So usually for the pure gas phase, I get better results with the backboard time discretization. And it seems like for the volume of fluid, I get better results in OpenFOAM with the Craig-Nicholson scheme. I'm not entirely sure why, but at least this seems to be my experience. But I haven't run that many VF simulations.
How do you run the two phases? Which software do you use to run the two phases flow?
Usually just the standard compressible interform.
Maybe I will give a suggestion about you go to the I will not talk about the modeling. You can just go to the FV solution. There is a C alpha there. That C alpha controls the artificial compression extent, how much sharpening of the interface. My experience is that term is very sensitive to the accuracy and to the stability for the very refined grid. I don't recommend to 1, maybe 0.5 to 1 is better. Yeah, you can try that. Yeah.
Okay, interesting.
If you use
Thanks.
the standard interval. Yeah.
Okay, thank you. Any other questions? Okay, so Bosen, for this method, is it possible to or have you tested, or have the plan to test it for fully compressible flows, for example, like a shock impact water droplet or few droplet? So in that case, it belongs to actually a fully compressible flow, right?
Yes, like a fully compressible flow. You are right, Paul. This is the point. It's ongoing. Our collaborations with the University of Sydney, we are doing that, and mainly for the scenario is where the big pressure difference occurs for the spray nozzle, and we see the choking. As a nozzle exit. Okay. And as I know, OpenFOAM provide a compressible interval, and but for our case, I would say for this model, there is still some issues there, where the compressibility of the flow coupled with the interface. The OpenFOAM provide algorithm, but I'm not sure the sub volume. This is still ongoing. I'm not doing it by myself now, but the students there is doing there. Okay. The sub volume scales, sub volume flux models, sub volume viscosity model, and even the surface tension models need to include the compressible effect. This is not easy. I would say. To be honest, I cannot give a very direct answer of this question. Yeah. Okay. Yeah. So looking forward to your progress in this direction.
And another question is normally, you know, prediction of refinement. So I'm not sure in your work you use a uniform mesh or adaptive, static mesh or adaptive mesh.
We use a static mesh because the AMR usually uses for the algorithm to resolve the interface. We don't resolve the interface, and in the long term run, I aim to couple the interface flow with the single phase flow, and we want to do it in a robust and in a practical view. Yeah.
Okay. Yeah. Okay. Thank you very much. Yes. So any other questions from the panelists and also the audience? Okay. Okay. So if no more questions, I would like to thank the speaker again, and I also encourage all the panelists to open your camera and join me. Thank you, Professor Bosen Wang from Beihang University. Okay. So if you in the future, if you have any, you still have questions with the talk, you can contact him directly. Okay. So
yes.
Yes. Okay. So
okay. Thank you, Wang.
Yeah. Thank you, and see you soon. Bye bye.
See you.